So far, all of the problems we've solved have involved the conservation of energy. Now, that usually means that there's some kind of frictionless surface, some ideal surface, which doesn't really exist in the real world. Or maybe we're launching something into the air and there's no air resistance, so we say. But what if we have a more real-world scenario where there is friction, like this? Right? So here we have a spring with spring constant 530 newtons per meter, and it's compressed 18 centimeters from the resting position. So I've already shown the givens. Here's 18 centimeters. So it's compressed, and then it's released, and it goes flying forward. But before releasing, we take this 24-gram block and we place it on the end of the spring. The coefficient of friction between the block and the surface, is 0.182. We have to find the block's speed when it leaves the spring at this point. So now the spring is back to its equilibrium position here, and the block is flying off. So here are the givens. I've written them down. To modify the equation of energy conservation, we can modify this equation to account for friction, and here's how we do it. We say that the initial energy, right, of the system at this point, well, let's first just write down the energies. At the beginning, all we have is 1/2 kx squared, like that. And at the end, all we have is 1/2 mv squared, because there's no more spring energy. Oops. We have 1/2 mv squared because the spring is not compressed, there's no spring energy. This whole thing, this whole process occurs at the same height, so there's no gravitational potential energy that we have to worry about. We could just say that this, whatever height it's at, is the zero level. So really we're just transforming some spring energy into some kinetic energy. So here's how you write the equation of conservation of energy modified to contain what's the energy that's being dissipated by friction. What we say is, we say the initial mechanical energy plus the work done by friction equals the final mechanical energy. There we go. So if you look at this equation, the work done by friction is always a negative value because friction always, it tries to slow objects down. Right? So the force of friction is always going to point in the opposite direction of motion, which means that theta, the angle between the friction force and the direction, or the distance, d, theta will always be 180, and the cosine of 180 is always -1. So this is always a negative number. So basically what we're doing here is we're subtracting away some of the mechanical energy at the beginning because friction takes it away. And so the final mechanical energy will be less than the initial. So to write down, so now that we have our equation, we can plug in the initial mechanical energy on the left. It's just 1/2 kx squared. Whenever we're on a flat horizontal surface, right, the work done by friction is -mu mg times distance. Here's why that's true. Work is F d cos theta, and of course this is the friction work, so we put an F sub k for kinetic friction. The kinetic friction is equal to mu times mg whenever you're on a flat horizontal surface. That's what we have here, flat horizontal surface. So this becomes mu times mg. The reason is because the equation for friction is mu times the normal force, and on a flat horizontal surface, the normal force equals mg. Then we have d, the distance traveled, and then we have cosine of 180, since the friction force pulls in the opposite direction as the distance traveled. So this will always be 180 when we're dealing with the force of friction. So we could just replace this with -mu mg times the distance. Okay, so that's the left side of the equation. We fill out the right side, which is the final energy, and it's only the kinetic 1/2 mv squared, like that. And what we can do then is plug in our values and we can solve for the final velocity, v. Right? You could write v final if you'd like that. But there's only one v, so you don't really need the subscript. Okay, we plug in. K is 530. X is, it's 18 centimeters, right, like I've shown. But make sure you convert to meters. So that's 0.18 squared plus a negative, mu is 0.182 times times mass first, 0.024. I already converted that. Whoops. Let me rewrite this a little bit neater. So there it is. We have mu 0.182 times the mass 0.024 times 9.81. And how far forward is our block moving as friction pulls it back? Well, the distance here is 0.18 meters, because friction pulls it as it moves 0.18 meters back to the resting position, or the equilibrium position. So this is 0.18. And these are all dots for times. Multiply by, multiply by, multiply by. Okay. All of that, and I'm out of room again, as always, is equal to 1/2 m. The mass is 0.024 times v squared. So let's solve for v and see what we get. And yikes, this comes to an impossibly high number. Let's see, what is the value we get? Looks like it's going to be 267.5 meters per second. That would never actually happen. It'd be hard to get a block to move that fast. So this is not a very realistic problem, but that's okay. We can see how to solve. So for sig figs, it would just become 270 when we round with sig figs. And that's how you solve. The important thing is that it's the exact same problem as before. You have ME initial, the initial energy, equaling the final energy. It's just that now we have to include this extra term on the left, this negative work being done by friction, because some of that initial energy gets taken away, it's dissipated by that negative work. And that's why we include this work term. So that's how you solve problems involving conservation of energy when there is friction involved.